In this video, I'm going to show you how I used long exposure photography and star trails to determine the duration of the sidereal day. Or at least how I tried to. So let's head over to past Keith of last night, who was trying to get long exposure photographs of the night sky. So the 𝗟𝗶 Family Astronomical Society is in action. Here's our 𝗟𝗶 Mount Telescope pointing towards Jupiter. Over there is the Equatorial Mount Telescope pointing towards Jupiter. And right here's a funny little thing. It's just a mobile phone camera pointing at the sky, mounted on a tripod. That's all it is. And you might just be able to make out a few dots here of stars. Not very easy to see, but in the settings I've turned the ISO right up to full and the camera exposure time, synthetic exposure, right up to full, focus to infinity, and I've got myself a little clicker. Let's just get it out. 1 second. Here it is. A little device that allows me to remotely trigger the camera so I'm not touching it. And what I'm going to do is I'm going to press that button and take a long exposure photograph that's only a minute long. I can only do a minute long, that's the maximum, of the sky. And once I've got a minute long exposure, I'm going to do another one, then another one, then another one, another one, another one, another one. I'll get as many as I can reasonably get. Now I've got the camera pointed towards Polaris, so you should be able to see some of the stars around it in the field of view moving relative to Polaris, and hopefully I'll be able to make some measurements from that later to determine the sidereal day. Look, I accidentally pressed the button, so it's already recording there, but it would be picking up all this red glare anyway, so it doesn't really matter. So that's the plan. Essentially, every time it finishes, I press the button and it starts again, and I'm going to get as many pictures as I can just like that. I'll show you the pictures later. I'm just sat out here enjoying the good weather, the stillness, watching this little thing go around, and every time it finishes, every 1 minute exposure, I'm pressing the clicker again to make another video, another long exposure image. I don't know if the results will be any good, but it's nice and pleasant to be sat out here anyway. Around it goes. As soon as it finishes, I'll press the button again. Press it again. There we go. Rinse and repeat. I might move the camera in a bit to see if I can get some different stars. But that'll do. As you can see, Past Keith struggled because the app that Past Keith was using only allowed exposures of up to 1 minute. And then messing around with the camera settings was challenging. So I've got the long exposure photographs, or 1 minute long exposure photographs. What do I do with them? Well, this is what I do with them. I look at them. And you can see not very much. If you've got dirt on your screen, it can be difficult to spot the stars amongst the dirt. There's perhaps a star here, perhaps some stars around here, but it is difficult to see. Now, I used one of the apps that you can use to look at constellations and try to figure out which of these stars corresponded to which constellation. Some of them are obvious, some of them are less obvious. So in terms of the obvious one, we've got the part of Ursa Major here, and I think those are the other stars for Ursa Major. We've got part of Draco, which goes off there, and part of Ursa Minor there. You can see they kind of correspond. Yeah, if I flick them on and off, you can kind of see where they correspond. Then that would make this star over here Polaris. I think there is another pale star quite close to it, but I think that one's Polaris. Then what I did is I used the software that's built into the phone to adjust things like the contrast of the image. I didn't use any fancy image editing software, just the stuff that's built into my phone to make the dark backgrounds darker And now you can see the stars a bit more clearly against the dark background. Again, they might be a bit pale to see on this screen, especially the resolution I'm recording, but they are there where there are vertices connecting these lines. That's where I could see stars. Okay, and this star up there is Polaris, as I said. I took a few of this image, and then I took another image. I moved the camera so Polaris was to the right of the field of view instead, and I got this image. Again, quite difficult to see, but you can probably make out we've got Cassiopeia there, very distinctive. Over here is Polaris. So again, mapping with the software to try and work out what the constellations are. There they are. That's part of Ursa Minor on the right. A little bit of Draco creeping in there. I don't know if you can see the stars. Cassiopeia, very obvious. Cepheus is there as well. I think that's fairly obvious, although again, the screen resolution might not make that visible. And a bit of Perseus up there as well. Make it darker using that built-in software on my phone. And you can see those are the constellations. And what you can probably see, hopefully see, is that those that are further from Polaris, the lines look longer, and those that are closer, the lines look shorter. Now, it is only a 1 minute exposure, which means the angular displacement of this arc of a circle up here is going to be less than a degree. In fact, it's going to be closer to 1/4 of a degree. There's Polaris. So we're going to be trying to measure angles of about 1/4 of a degree. Now, if I printed this out, got a piece of paper, drew on it, whipped out a protractor, I would struggle because I can only measure to the nearest degree with a protractor. What I could do, of course, is make some measurements and use trigonometry, and that's exactly what I did. Or if I had a better camera, a proper digital camera, where I could increase the exposure time, then I could increase the exposure time to, let's say, 40 minutes. Now, with an exposure time of 40 minutes, that means that if I can measure to the nearest degree, I would have about 10% uncertainty on the measurement of that angular displacement of the stars around Polaris. 10% uncertainty is still not great, especially when we're trying to calculate the sidereal duration, which is only 4 minutes shorter than the solar day duration. So it's the mean solar day duration. So it's a bit... A longer exposure is better, but even then, just grabbing a protractor and measuring those angles is not really the way to go. We're going to have to use trigonometry. So using trigonometry to analyze star trails, and I spent way too long on this animation, so I'm going to show it. Here is analyzing star trails with a picture in the background that I stole from Wikipedia. Look at it zoom in. Oh, so proud of that. We're going to do that again. Zooming out. Look at this, zooming in. What a PowerPoint Pro. Okay, I'll get on with it. There's the picture we're going to analyze. And we're going to start by looking at some stars that are bright enough that I can see them clearly in Ursa Major. And I'm going to start with this one. Not sure how I pronounce the name of this star. I'm going with 𝗟𝗶. It's probably not 𝗟𝗶, but I'm going with 𝗟𝗶. It's the brightest star in the constellation of Ursa Major. And Polaris is there. So let's zoom right in on those two stars, and you can see that Polaris is a dot, but 𝗟𝗶 has a bit of a line to it. Now, how am I going to use trigonometry here? Well, what I'm going to do is to... well, I'll show you with a diagram. If the green blob is Polaris, and the red line is the arc, you notice it's a little bit curved, is the arc of 𝗟𝗶, then if I measure the distance from Polaris to the middle of that arc, and I measure the length of that arc, now I know that it's not actually going to be a straight line, but over the small angles we're talking about, it might as well be a straight line. I end up with these two measurements. Let's call the distance from Polaris to the center of that arc d, and let's call this distance, pick a letter, x. Let's just call it x. We end up with a right-angled triangle. the right angle would be this part in the middle here. That's the right angle. And you can see the right angled triangle there. D is this distance there, and x is this distance here. So half x is this little distance there. And so using trigonometry, the tan of this angle, the tangent of this angle, is half x, that's this length here, divided by d, that's this big distance up there. So that's what I'm going to do. How am I going to measure x and d? Well, I need a piece of software that allows me to count pixels. And I don't have any fancy software. So I used Microsoft Paint. That's right, I used Microsoft Paint. There's nothing wrong with using Microsoft Paint. I zoomed right in on the interesting bit of 𝗟𝗶. There it was. I drew a line with that lovely line tool, and in the bottom left you can see that we have the horizontal displacement and vertical displacement in pixels of that line. It's 9 across and 18 high, so we can use Pythagorean theorem to work out the length. It's just going to be, in this case, 9 squared plus 18 squared, all under the square root. So when I do that, it will give me that distance x. I also have to know the distance between the centre of this arc. Let's just move back a little bit. The centre of this arc here and the centre of Polaris. And if I know the positions of those, I can use Pythagoras again. So let's go find the centre of Polaris. There's Polaris. Zoom in so you can see it. There's Polaris, and if we have a look down here, that is actually the position of Polaris. I put the cursor directly over the centre of Polaris, and that showed the position of the cursor. When I took a screenshot, the cursor vanished, but the cursor is basically there, the centre of this blob, and that's what gave me the 34 pixels from the top left and 59 pixels from the top left. So 34 across, 59 down. I had to do the same thing for the centre of the 𝗟𝗶 smudge. So I placed the cursor right in the middle of the 𝗟𝗶 smudge, about there. And if I zoom right in, you can see the coordinates of that position of the 𝗟𝗶 smudge. So then, I don't know if it's pronounced 𝗟𝗶. It's going to be really embarrassing if it's not. So there you can see the positions on the right. Let's do some maths. The arc length of 𝗟𝗶 smudge was 9 squared plus 18 squared under the square root. In pixels, it was that. I did everything to 4 significant figures because the number of minutes at the end of the sidereal day, I'm going to be measuring in minutes to the nearest minute. Radial distance from Polaris to the middle of the 𝗟𝗶 smudge. So that was the horizontal displacement, and that's the vertical displacement. You can see what I did there. From the centre points there, 1,869 subtract 34. That's how far to the right we've gone from one to the other. And 1,033 subtract 59 is how far down we've gone from one to the other. And so square of those two, add them together, take the square root. The distance between them is, in units of pixels, 2,077 pixels. Now, the tan of the angle is equal to the ratio of half of 20.12, which is 10.06, divided by that distance between the centres, which was 2,077. So 10.06 was half x, and 20.77 not 20.77, 2077 was d, going back to that trig diagram that we had before. So 10.06 is half x, just like that, and 2077 is big D. Oops, moving all over the place. Where am I supposed to be? There. Okay, so if the tan of the angle is that divided by that, then the arctan, on some calculators that's written as tan to the minus 1, not on my calculator, of course, because I've got a brilliant calculator, an HP 42, doesn't matter. But the arctan of that ratio of distances is the angle. And look, it's about 1/4 of a degree, which is what we expected. Maybe a tad larger than 1/4 of a degree. So what proportion of a full circle, which is what you'd get in a sidereal day, is about 1/4 of a degree. Well, it's 300 and, well, it's that divided by 360. So how long is a full day? Well, it took us 1 minute to get this angular displacement. So the full angular displacement across a full sidereal day divided by that should be the length of a sidereal day divided by 1 minute. Multiply both sides by a minute, we end up with this. So 360 degrees is one full day as an angle, divided by the 1 minute's worth of angle, times by 1 minute, gives us, well, in this case, it was 1,297 minutes, which works out to be 21 hours and 37 minutes. Now, that's a tad too small. Ought to be bigger than that. So why was it too small? Well, I started the line just where the pixels went a little bit lighter and ended it just where the pixels started getting lighter. But actually, if you have a look, the stars themselves, even single stars, have some sort of size to them when you look at them. And I think that's because of what we call saturation of the pixels. Enough light lands on one pixel, it spreads to the pixels next to it. So brighter it is, the more that happens. So I haven't taken into account the size of the star on this screen. And we can have some sort of estimate of the size of the star because you can see the width of the smudge. The stars have width on the screen and the smudge has a width on the screen. So I need to take account for that. So what did I do? Well, I move to the next slide. There we go. I redid it somewhere else. And you can see there I've redone it so that we're a little bit further in from the very edge. And it's just a bit of a guess. I don't really know exactly where it should be, but I went with there and I took 2. And I decided I'm going to do 2 readings, one at the very edge, one in a bit, for each star that I analyse. And I did the same thing. So exactly the same analysis. I won't go through how I got these data again because you've seen it once. The middle of the smudge distance hasn't changed, but the length of the smudge, that's a little bit shorter this time. And that gives me a slightly longer sidereal day. So I look at those two and I say, well, I'm getting about 24 hours. It works out to be pretty much bang on 24 hours, 1,440 minutes, 1,440 minutes. And I've plotted a lovely graph there to show the mean sidereal days, mean sidereal day in minutes versus the number of stars I've analysed. And the red dotted line is what it should be. You don't do science like this. You don't have the target in sight and then just get data until you get that answer and then stop. That's bad science. It leads to false positives and things. You don't do that. But this is just a GCSE Astronomy Observation. So I thought, let's at least know where we're trying to get with this. And there's our data point there. So let's pick another star. And the star I've picked is Merak, or the second brightest star in Ursa Major. And I did exactly the same thing. So you can see the positions of the 2 stars, the Smudge and Polaris. Polaris top left, Smudge is the one on the bottom left. Then the line drawn for Merak is there with the coordinates that I read straight off Microsoft Paint. Chucked the data in. I got a rather tiny 15 hours and 31 minutes. That is nowhere near big enough. Something's gone wrong. So let's look at another 2 positions on Merak, because that is way too low. So let's look at another 2 positions. And I went a little bit in, and you can see that there. Went in a bit. And I got a massive number, 31 hours and 8 minutes. Pluck those numbers into this list. Well, I've forgotten the units there, but you get the idea. And woof! The mean sidereal day, which was a little bit too high, is now way too low. 23 hours and 40 minutes when you calculate the mean of all 4 of these data points. Now it's too low. So I've got to do another star. Not so I've got to do another star. I should be doing other stars anyway. So let's do some more stars. Let's do Phecda. That's probably how that's pronounced. Phecda. or Festa, maybe. I'm going to go with Fecta. That is the third brightest star in Ursa Major, and so I used that star. Same thing I did last time. I'm not going to show the analysis again. You saw what I did, and I got 26 hours, 33 minutes. And then I did another 2 points for Fecta. So that was the first 2 points on the smudge effector that I did. And then I did the second 2 points, and you'll notice the numbers changed slightly. Not a huge amount, but they changed slightly. Bring, there we go. Now it's down to 22 hours and 29 minutes. And I can add that to that list of averages, and I get 23 hours, 57 minutes. Is getting closer to that red line, exactly what we want it to do. Excellent. So let's do another star. And so I then decided to use the other picture. Now, I've got loads of stars that I could have chosen to do on that first picture. But I took lots of that first picture, and that was the best one. And I took loads of a second picture, or I changed the camera to a second position. So let's use that second one. And that's what I did. So, oops, press the wrong button. So here's the second picture. Polaris is there. There's Cassiopeia in the middle. There's 𝗟𝗏, I think. I'm not sure if that's 𝗟𝗏 or not. I wasn't clear. But it doesn't matter what the star is. It really doesn't matter. We're just using it. Same process as last time. I won't show the steps. Got the arc length in pixels of 𝗟𝗏. We got the distance from the center of the 𝗟𝗏 smudge to the center of Polaris, ran through the maths, and got a whopping 32 hours and 55 minutes. Oh dear, it looks like I chose 2 points that are too close together on the arc of 𝗟𝗏. So let's take 2 more points, maybe at the extreme ends of where it's the smudge is. I did that. I got 14 hours, 50 minutes, swinging all over the place. Yes, the mean is now 23 hours, 56 minutes, which is all very nice, but we're swinging all over the place. Look at these numbers. The uncertainty is huge. Remember, the uncertainty would be half the range. Is absolutely enormous. So what would I do? I would do more stars. I've just picked 4 stars so far. I would do as many as I could do, and I would spend all day long, maybe a few days, just analysing star after star. It's a sort of task that AI should be good at, but I wouldn't trust AI to do it because it would make up stars. So that's the approach that you use, and the more stars you do, the more accurate your answer ought to be. That's the benefit of using more and more and more stars. The other advantage, the other improvement that we could make would be using longer star trails. But I can't use longer star trails on my particular phone with that particular app because it didn't allow me to do it. Now, I did have a look at some other apps. I actually looked at the default app that was built into my Android phone for taking photographs, and it did allow for longer exposures, 5-minute exposures. That's more than a degree of the angular displacement of the star. So I thought, this is great. Let's do that. The problem is that app automatically rotates the image and stacks it afterwards, which isn't exactly what I wanted to do. And when I did that, I ended up with a picture that looked like this, which looks great. I can't do anything with it for star trails, though, but look at this. Just by pure luck, I happened to get a meteor in my picture. Apropos of nothing to do with this topic, but how about that meteor? And when I tried to make the darks darker and things, you can see the sky there. It's a little bit clearer what the stars are doing. You've got the Pleiades over here, or Pleiades as I prefer to pronounce it. You've got over here is Orion. You've got Orion's belt there. It's difficult to spot now because the difference in brightnesses have all been flattened out. I think that's Jupiter there. And you can see here we've got the Orion Nebula, and that is a really clear, beautiful meteor. And that got me thinking, oh, by the way, that's the Orion Nebula where my hand cursor is, right there. So that's with a mobile phone without any special optics, without any sort of magnifying optics. So that got me thinking, it should be possible to do a bunch of long 5-minute exposures during a meteor shower and see
identify the position of the radiant of the meteor. Because in a meteor shower, you can get a meteor every half a minute. So that over 5 minutes could be potentially 10 meteors that we would see in a picture, and we could extrapolate them back and find the radiant. And that'd be a really lovely aided observation to do. So next time there's a meteor shower, I'll keep an eye on it. I'll do that when it's good weather and there's a meteor shower. I'm going to do that observation. But not now. So that's how to use star trails to determine the sidereal day. Hopefully that was helpful.